Alright, so why? Why do we have to go through all of this work for balancing chemical equations? The best answer is because of the law of conservation of mass. Now, some of you could probably already tell me what the law of conservation of mass is from experience or just from the title. You know the law of conservation of energy from probably other classes. The law of conservation of mass. What does that mean? Matter cannot be created nor destroyed. So we gotta say where it's going. When we're talking about matter, we're at the atomic level at this point. So we have to tell where it's going. All the atoms went in a chemical reaction. And that's why we do all this stuff. And we show chemical reactions using chemical equations. Chemical equations are kind of like a recipe. I'll pause there for a second, make sure we haven't gone too fast. How many of you have ever followed a recipe before? So what did you have to do when you followed your recipe? You had to probably measure, right? You had to measure things out. What happens if you don't use the right amount of... It's not going to be right, okay? And that's where we get this. The chemical equations are like a recipe. It tells us what goes into the substance and what's going to come out. So, it's like a recipe, there's ingredients. So, when we look at our chemical equations, we have reactants. And those are kind of like your ingredients. That's what comes in. Okay? That is what you start with, what is changed. So ingredients might be enough for you, but it's up to you. They're your notes. And reactants are always on the left. Okay? Reactants are always on the left. It's really important. And then you put your ingredients in, you put your reactants in, and you come up with something. So in a chemical reaction, we're going to come up with products. So what you made, or what is made. Okay, think about if you've ever made a cake. You put in flour and eggs and oil, sugar. Are those reactants the same as the products? Cake is good to eat, right? But if I give you a bunch of some raw eggs and flour and cocoa all mixed together, you might not want to eat that. That's not what you wanted. So what goes in is not what comes out, and that's kind of the come away from that. So what is made? Products are always on the right side. Okay. Products are always on the right side. It's important. What's in the middle? You guys have seen these before. This isn't very new information to you guys. When I look at a chemical equation, we have reactants, and then what's in the middle? For making something, it's put it in the oven, put it in the refrigerator, let it sit, let it chill. What is the middle? We have this. So this arrow it is the yield sign. You could also say becomes, okay, or reacts with, or so reactants go to products. Ingredients yield what is made. Okay. Starting material becomes something else. Okay, so that's how you would read that. Let's look at an example really quick. 2SO2 Alright. So in this example, we have 2 reactants and we only have 1 product. So we put 2 things together and we came up with 1 thing. Alright. Now, what does this little G mean? Do you guys know? Nobody knows what that little G means? This right here, it means the state. Okay, so what state of matter starts with a G? Gas. Okay, so that means that this sulfur dioxide here is in a gaseous state. That means we're going to put, and then the oxygen is in a gaseous state. So we're putting 2 gases together. Alright? So what does the little L mean then? It means liquid. So that would mean that the state of matter that your reactants or products were in were that. What does the little S mean? Solid. Alright, yeah, you guys are kind of getting the idea there. Now the one that's a little bit weird that you might not be familiar with is AQ. I know that looks really weird. But AQ means aqueous. And that just means dissolved in water. Okay. So So you're going to see the states of matter on the reactants and on the products. And that just tells you how your recipe needs to go. Like sometimes you get told to melt the butter and sometimes it needs to be solid. It's the same idea. How does my material need to be in order for my recipe to go off correctly? Now just like a recipe, the yields, like sometimes you're going to throw it in the oven, sometimes you're going to put it in the refrigerator. Sometimes you need a little help. So sometimes you will see your yield sign like this, and I have a little triangle on top. Does anybody know what that means? Okay, that means heat is added. So just like when you cook it, you got thrown in the oven or something. Maybe for chemistry it might be a Bunsen burner or something like that. Okay, and then there's another example that you're probably going to see when you do your CK12 practice. And it's not always going to say PT, but it'll have an arrow with something over top of it. That means there is a catalyst. So we need to think about this word for a second. Catalyst used or catalyst added. That means something made the reaction go faster. So in this case it would be platinum. You might have anything else. It might be an enzyme, anything that might make the reaction go faster. Alright. One more thing and then we'll do some, or 2 more things and then we'll do some practice on that. I'm gonna get another color. We look at our example here. What is that called? Nobody knows what that's called? Okay, let's talk about the numbers that are here. Alright, coefficients and subscripts. Coefficients. Okay. Coefficients are the big numbers. That's a terrible R. They tell how many molecules or moles. Now that's a pretty, those are two completely different things, but we're going to put them in the same line here. Needed. We will probably never ever look at a reaction and just look at a single molecule of anything because they're so tiny. But we could look at a mole. Like I can hold 12 grams of carbon in my hand and I can see how I can measure that out and use 1 mole. So what we really need to grab onto this idea, because the next unit we're doing is stoichiometry and we're going to need to use this concept. We talked about moles in the last unit, but trying to make sure and remember that the coefficients tell us how many moles are needed. And we can change coefficients. That'll make a lot more sense when we get to using our examples. And we're going to look at subscripts. Subscripts are these little numbers right here. Okay, so they tell how many atoms are inside the molecules. We cannot change them. Okay. Because if we change them, that's going to change the material we have. Alright, so we'll come back to all of these ideas when we do a couple of examples. And then I'll let you go. But I'm going to turn the page. Now, that's a bunch of stuff to think about, but now you're going to have to actually balance them just like we did the other day in the example with the visual. But we're taking away the visual. So here's the steps to balancing a chemical equation. Number 1, make an inventory list. Number 2, count your atoms. And we're going to do that by multiplying the coefficient times the subscript for each element. And then you can change the coefficient. I feel like this is super boring today, but got to get through it. For 1 element or molecule. count the atoms again. To check if balanced. Balanced is where they check and see if they're the same on the reactants and the product side. So we'll go through those examples. 5. Change the coefficient. This is the last one. Repeat 4 and 5 until balanced. Alright, so let's do an example. If I give you B2 plus W2 yields BW3, we're not talking about chicken here. Alright, what do we gotta do? We'll first make an inventory list. So, alright, what elements do I have? I have B's, and I have W's, and then I need to say how many do I have in the reactants, and how many do I have in the products? Well, in the reactants, I'm gonna count the atoms, multiply the coefficient times the subscript. Well, there isn't any coefficients yet, so I am just gonna see the subscript. I only have 2 B's here, I have 2 W's, but then in the product side, so if I come over here, I only have 1 B, but I have 3 W's, because that subscript tells me how many of these atoms I have. Well, they don't match. So I'm gonna change. Let's see. I see that I have a 2 and a 3 here. I know that I'm gonna have to get to some number that is like a common denominator almost, using that kind of thinking. So I am gonna go ahead and I'm gonna put a 3 here, and I'm gonna recount. So 3 times 2 gives me 6. And I see that doesn't count, so I'm gonna go ahead and put a 2 here. 2 times 1, because this is a compound, so we have to count for everything in the compound, is 2. 2 times 3 is 6. Okay, so then I look, I count again, so that's the count again. 2 B's, 2 B's, 6 W's, 6 W's. So now my reactants match my products. Give me a thumbs up if that makes sense and you feel like you can do that. Okay, alright, let's go ahead and do one more that's a little more difficult one that you kind of have to persevere with. So sodium and water yields sodium hydroxide plus hydrogen. Alright, first thing we do, we make an inventory list. So what elements do I see? I see sodium, I see hydrogen, I see oxygen. Alright, and then I say, well, here's the yield sign, so I need to look at the reactants and the products. I have 1 sodium in the reactants, I have 2 hydrogens in the reactants, I have 1 oxygen. In the products, I have 1 sodium, now be careful here, I have 1 oxygen, but my oxygen's in this row. And then hydrogen gives me a problem. I have 2 hydrogens here and 1 hydrogen there, so I have 3 hydrogens total. Okay. Well, the first thing is, okay, so I know that I can only get hydrogen from this one. So somehow I'm going to have to use that same thinking, common denominator thinking, to get them to match. So I'm going to start with, I'll put a color so you can see what I'm doing. I'll put a 3 here, and I'm going to recount. So count the atoms. 3 times 2 gives me 6, but I think I need 3 times 1 because this whole compound is affected by that coefficient. So that gives me 3 oxygens. Sodium I didn't change because I didn't give it a subscript. So then I think, well, what did I think there? I'm going to put a 3 here because my oxygen needs to match. I'll show you how many times I change it. So 3, now I have to affect the whole compound. 3 times 1, that gives me 3. 3 times 1, that gives me 3. Be careful with hydrogen. 3 times 1 gives me 3, but I still have these 2 over here. So I'm going to have 5. Well, that's not going to work because I can only get multiples of 2 over here. So this is where that perseverance comes in. We have to continue trying. So I'm going to go ahead and change this to a 4 because I know I need it to be an even number. So recount. 4 times 2 is 8. 4 times 1 is 4. Okay, and if I make this a 4, I'm going to recount again. So I'm going to get 4 here, 4 here. Alright, we're making some progress. And then this hydrogen business. 4 and 2 is only 6. Well, I've just messed it up all over the place, right? Not so, because notice we have 2 here. Do 2 times 2. Now I have 4, and 4 times 4 is 4, so 4 plus 4 is 8. Now I match. The only thing left is the sodium over here. So I'm going to put a coefficient here, and multiply 4 times 1 gives me 4. So that one took a lot of perseverance, but we can push through. Now, next thing. 4, 4, 4, and 2. Could I reduce that? Yeah, I could divide them all by 2. I know. Should have done that in the first place, right? Maybe, but sometimes when you're working these, you have to go through the whole process. So this would be a 1, this would be a 2, this would be a 2, and this would be a 2. And you might say, well, why didn't you just start with 2? Because I had to think through it. You super geniuses probably could have seen, oh, if I just do a 2, and that's fine. If you can jump right to the right ratio, perfect. Okay? If you have to struggle through, that's perfect too. Sometimes you have to do that perseverance just a little bit to get through these chemical equations. Alright, I'm going to stop talking and